Hello friends, this is my second lecture of electrochemistry, and in this chapter or in this topic I will cover conductor, non-conductor, electrolysis, electrolytic conductance, factor influencing the conductivity of electrolytes, Coulter's law and Faraday's law. Okay, we all are known about that electrochemistry deals with the study of electrical properties of solution of electrolytes and with the interrelation of chemical phenomenon and electrical energies. Okay, now what is the conductor? Conductor and non-conductor. Okay, conductor is subdivided into types: metallic conductor and electrolytic conductor. Okay, and at first we will say that conductor, the substance which allows electric current to follow through them is known as conductor, and it may be metal, aqueous solution, etc. And non-conductor, the substances which do not allow electrical current to pass through them is known as non-conductor. Okay, and there are some metallic conductor and electrolytic conductor. There is a difference. And in electrolytic conductor, there are two types of electrolytic conductor. Electrolytic conductor is strong electrolyte and weak electrolyte. Okay, strong electrolyte, the substances which can completely dissociate in aqueous solution is known as strong electrolyte, and weak electrolyte which is not completely dissociate. Like if we say that NaCl, it can completely dissociate in aqueous solution, that is Na plus Cl minus, this is complete dissociation. If we take 1 mole of NaCl, then it will be 1 mole of Na plus, 1 mole of Cl minus. But if we consider that a weak electrolyte like acetic acid, such type of electrolyte is weak electrolyte, it can convert is in this way, that acetate CH3COO minus plus H plus, and if we take 100 mole of acetic acid, then if we get only 2 mole of acetate or 2 mole of H plus ion, then what happened? Amongst the 100 moles, it will dissociate only 2 mole. So, or 3 mole or 5 mole in this way. But from the 100 mole acetic acid, we are unable to get 100 mole acetate, 100 mole H plus. So, this type of electrolyte is known as weak electrolyte. Okay, and what is the difference between metallic conductor and electrolytic conductor? Metallic conductor flow its electricity by electrons. Okay, that's means flow of electricity takes place without the decomposition of the substances. For metallic conductor, the flow of electricity takes place without the decomposition of the substances. But electrolytic conduction, for electrolytic conduction, the flow of electricity takes place by the chemical change of electrolytes. This is the chemical change. Okay. For metallic conductor, no transfer of the matter takes place. Or metallic conductor কোনো matter transfer হবে না, অর্থাৎ substance remains in the same position, but electron flow and it can carry electricity. Okay, but transfer of matter takes place for the electrolytic conductor. That means ion can carry charge, so ion can movement in electrolytic conductor. And in metallic conductor, the resistance to the flow of current increases with the increase in temperature. Okay, resistance increases for metallic conductor, but when temperature is increases for the electrolytic conductor, the movement of ion will be increased. The movement of ion will be increased, and for this reason the conductance will be increased. Okay, and now what is the electrolysis? What is electrolysis? Electrolysis is the process. What is this? This is a process. The process of decomposition of an electrolyte by the passage of electricity is called electrolysis. What is this? The process of decomposition of an electrolyte. This is the electrolyte decomposition. That's mean NaCl. So by electricity, if it can decompose, that's mean Na plus Cl minus. Okay, so this is the process of decomposition of electrolyte by passage of electricity is called electrolysis or electrolytic dissociation. So it is electrolytic dissociation. Okay, now like what happened in electrolytic or electrolysis of a fused sodium chloride? If it is fused sodium chloride, then by electricity we can decompose like this. Okay, and electrolysis of fused sodium chloride, when the fused sodium chloride is electrolyzed, Na plus ions moves towards the cathode. That's mean when it is electrolyzed, then what happen? If we consider NaCl, okay, if it is in molten condition or in electrolysis, then there will be a positive and negative charge. If it is cathode, if it is anode, okay, then the positive charge, that is sodium, it will move towards the cathode and this will move towards the anode. Okay, and it will be free in cathode and in anode. Then in molten state, that's when if there is no water, then this process occurs. If there is a water, that's when water solution or aqueous solution of sodium chloride, then the dissociation of water will happen and H plus ion moves to other cathode and OH minus moves towards the anode. Okay, so if we want to electrolyze sodium chloride, then we should take the molten state of sodium chloride or non-aqueous solution. That's mean only sodium chloride, fused sodium chloride. Okay, now so in this way, this is the electrolysis, and there are so many electrolysis processes. The electrolysis of water using the platinum electrode, acidified water can dissociate and it can free hydrogen. That's mean if water dissociate in this way, OH minus and H plus, then H plus ion moves towards the cathode and OH minus ion towards the anode. And what will be the product? The product will be H plus electron. It takes electron from the cathode and it will be H, then H plus H, it will be H2 and 4 OH minus, okay, 4 OH minus 4 electron equal to 2 H2O plus O2. So this is the process. Okay, so I'm not going to details about the electrolysis because so many electrolysis are there. Okay, now we are going to discuss about the conductance, electrolytic conductance, because in electrolysis there are so many electrolysis, aqueous sodium chloride, fused sodium chloride, aqueous NaOH, fused NaOH, aqueous copper sulfate, dilute sulfuric acid, aqueous silver nitrate. And what happened? If we use aqueous sodium chloride, then the product obtained in the anode is chlorine. In anode will be chlorine and in the cathode will be hydrogen. Not in the cathode, it is not sodium for aqueous sodium chloride. But when it is fused sodium chloride, then sodium will free in cathode and chlorine will free in anode. But in aqueous sodium chloride, H plus will free in cathode and Cl minus free in anode. Okay. So now we are going to the most important part of this chapter in electrochemistry, that's mean the electrolytic conductance. Electrolytic conductance. Now what is the electrolytic conductance? From the Ohm's law, we know the metallic and electrolytic conductors obey Ohm's law. Okay, and from the Ohm's law, we know that the resistance, or for metallic or non-metallic, there is no problem, but and it may be electrolytic, no problem, but the resistance okay, resistance, what is the resistance? The resistance R is directly proportional to the length of the wire, and R is the proportional 1 by A, or area of the, or inversely proportional to the cross section of the wire. Now if we consider it is an electrolytic solution, then what happens? Then what is the resistance? Is there any wire in electrolytic solution? If it is a solution, then is there any wire? Tar ache kono nei? So if there is a cathode and if there is a anode, then what happens? The distance between this cathode and anode is known as L. What is this? The distance between cathode and anode is known as L, and the area of the electrode which is deep in the solution, the portion which is deep in the solution, the area of this part of electrode is known as area, that is A, that is cross section. So what is the cross section for the electrolytic solution? Here the area of the electrode which is deep in the solution, and distance between cathode and anode is known as the path length, that is L. Okay. So from the Ohm's law, the resistance of an electrolytic solution, is directly proportional to the length, that's mean difference between cathode and anode, and resistance is also inversely proportional to the cross section of the any electrode. Okay, clear? And now combining these two equations, we can get L by A. Okay, now what happened? This is R, that is resistance, L is the length between two electrode, A is the cross section or the area of the electrode which is deep in the solution, okay, is equal to rho L by A. And what is this? R is the resistance of the electrolytic solution and rho is the resistivity. R is the resistance and rho is the resistivity. Okay, clear? So what is this? The conductance of a conductor is equal to the reciprocal of the resistance. That's mean we know that, we again know R equal to V by A. What was that? That is volt per current, or I equal to V equal to IR. That was the electrolytic conductor for metallic. Now if we are taking the electrolytic conductance, so R, what is the R? R is the resistance, rho is the resistivity. Now 1 by R, inverse of R equal to inverse of rho equal to into inverse of L by A. What happened? The inverse of R R was the resistance and inverse of R, which is known as conductance, inverse of R or reciprocal of the conductance is reciprocal of the resistance is known as conductance. So what I can write? I can write the reciprocal of resistance is known as conductance. Okay, reciprocal of the resistance is known as conductance. Clear? So what is this? That means this reciprocal is actually lambda. This is the capital lambda. This is a capital lambda, which is known as inverse of resistance or reciprocal of the resistance, which is known as conductance. The lambda equal to 1 by R, and what is this? 1 by rho. That's mean 1 by resistivity equal to specific conductance, which is known as kappa. Okay, so this is actually conductance, this is specific conductance, and 1 by L by A. And what is L by A? The L by A is known as which is known as cell constant, that is lambda equal to kappa into 1 by cell constant. Okay, what is this? This is the cell constant. Clear? So conductance equal to kappa, that is specific conductance, into 1 by cell constant, or we can write in this way: lambda equal to kappa into A by L. Okay, cell constant equal to L by A, then this is A by L. No problem. Now what is the unit of R? R, resistance, which is ohms. Okay, what was that? Ohm's law. From the Ohm's law, this is ohm, and inverse of this, that's equal to lambda is not a resistance, it is conductance, that is mho. Inverse of ohms, that is mho. Okay, so this is the mho, and what will be the unit of kappa? That is resistivity. Okay, sorry, specific conductance. So lambda into L by A equal to kappa. So kappa equal to ohms. This is mho into, this is centimeter, this is centimeter square. So centimeter square, there is 1 centimeter is cancelled out, then what happened? This is centimeter inverse. So mho centimeter inverse. Okay. So this is the unit of specific conductance or specific conductivity. Clear? No problem. So this is very important part of the electrolytic solution. Now the cell constant, what is the cell constant? We already know. Very important. Now we can say that what is the equivalent conductance? What is the equivalent conductance? Now if this kappa, or if the lambda, if lambda is the conductance, when the solution is 1 normal solution. When the solution is 1 normal, that's when 1 gram equivalent amount of electrolyte dissolved in 1 liter solution. And distance between these two electrode is 1 centimeter, and this is 1 normal solution, and area of the cross section or area of the electrode which is deep in the solution is 1 centimeter square. Then the conductance of the solution is known as equivalent conductance, that is equivalent amount. That's mean when equivalent amount of substance or electrolyte dissolved in 1 liter solution and the electrode, the distance between two electrode is 1 centimeter and the cross section of the electrode is 1 centimeter square, then the conductance of the solution is known as equivalent conductance. So we can say that the equivalent conductance is defined as the product of specific conductance and the volume in ml of the solution which contains 1 gram equivalent of the electrolytes. Okay, so what happened? That's mean what is this? That is actually lambda, that is EQ. What is this? When lambda is converted to capital lambda is converted to small lambda EQ, that is equivalent, equal to kappa into what was that here? L, A into L. Okay, but I will convert this portion in this way, that kappa, that is A into L by L into L. What was that? That is actually volume. This is actually area of the cross section, that is kappa into V per centimeter square, per centimeter square, per centimeter square. Okay, so what is the V? V means, that's mean V, what is V? That is 1000 by C or N. N means normal. How it is? That's mean centimeter, that's mean C gram equivalent remains in 1000 ml. C gram equivalent, if remains in 1000 ml, then 1 gram equivalent 1000 by C ml. So this is the volume. V is this. How? Because we know, if we consider N normal solution or C normal solution, then C gram equivalent of electrolyte remains in 1000 ml solution, then 1 gram equivalent remains in 1000 divided by C ml solution. So V is 1000 by C. So lambda EQ equal to 1000 kappa by C. So what is this? So lambda equivalent equal to 1000 kappa by C. And when the solution is molar solution, then lambda molar, that is molar conductance equal to 1000 kappa by M, that is molar solution. In this way, that's M moles per liter. Okay, if M mole solution remains in 1000 ml solution, 1000 ml, then 1 mole, that's mean M mole remains in 1000 ml, then 1 mole 1000 divided by M. So this is the V. So In this way we are considering the V per centimeter square. So we can write anyway that always we can write the equivalent conductance lambda EQ equal to 1000 kappa by C and lambda molar equal to 1000 kappa by molar. Okay, so this is the equation. And what will be the unit? The unit is, what will be the unit of lambda equivalent? That's mean ohm inverse centimeter square, ohm inverse centimeter square, okay, centimeter square per gram equivalent, per gram so this is the unit. This is the unit of this. Okay, clear or not? So this is the unit of equivalent conductance, and when it is molar conductance then it is ohm inverse centimeter square per gram mole. Okay, per gram mole. This is the unit of the conductance. Then what happened about the equivalent conductance and molar conductance? What is the relation between equivalent conductance and molar conductance? The relation between lambda EQ and lambda M. Okay, lambda EQ and lambda M. We know lambda EQ equal to 1000 kappa by normal or C, and lambda M equal to 1000 kappa by capital M molar. Okay, then we know that normality equal to n factor of molarity. N factor of molarity. What is this? Normality equal to n factor of molarity. You already know the sulfuric acid, 2 normal sulfuric acid. That's mean, what was that? That's mean 1 mole H2SO4 equal to 2 gram equivalent sulfuric acid. 1 mole sulfuric acid equal to 2 gram equivalent sulfuric acid. Okay, then 2 normal equal to 1 molar. Okay, 2 normal equal to 1 molar. That's mean normality is equal to n factor of molarity. Okay, so normality and molarity, what was that? The normality and molarity, since it is n and n factor, small n factor, then we can replace any one. Okay, if we say that normality by molarity, then what happen? Then we can write in this way, lambda m by lambda EQ, then what happened? 1000 kappa by n means n into m. Okay, sorry, आगे मोलर नियेছি, that is m divided by 1000 kappa by n into m. Okay, then what is this? This is actually 1000 kappas cancel out, then n factor, just n factor. That's mean lambda m equal to lambda m equal to just n into lambda equivalent. Clear? Lambda equivalent. Is it right? So lambda equivalent equal to lambda m by valency factor. Lambda m by valency factor. This is the valency factor also. Okay? And there is a factor influencing the conductivity of electrolytes. The first thing is that inter-ionic attraction. If the inter-ionic attraction is more, then conductance will be low. Okay? If inter-ionic, if one ion and another ion plus minus, if they attract to each other, they are not moving fast. Okay? For this reason the conductance will decrease. Okay? No problem. And then polarity. Polarity of the solvent. If the polarity of the solvent is high, then again that's mean conductivity will be more. Okay? That's mean easily they can dissociate, easily the electrolyte can dissociate and they can move fast. No problem. And if the solvent is more viscous, then conductivity decreases. For more viscous, conductivity decreases. Okay? And temperature. If the temperature is high, the moving of the particle, or that's mean kinetic energy of the particle will be increased, and for this reason the conductance also increase. Now there is a factor, one factor is very important here. What is this? The dilution. The dilution. There is a rule, that's mean when the root concentration versus conductance of the solution or electrolyte, for strong electrolyte with the dilution, in this position there is dilution, with the dilution the conductance will increase slightly in this way for strong electrolyte. When for strong electrolyte, if C decreases, that's when root C also decreases, then the conductance increases slightly. But for weak electrolyte, initially the conductance increases slightly, but when is very dilute, that's when this position is known as infinite dilution. At infinite dilution, the conductance is highly increased, that is jump of the conductance. Why? The conductance is very high in this position, or when the dilution is very high, that's been at infinite dilution, there is a complete dissociation of the weak electrolyte. At very dilute solution, that's mean at infinite dilution, the complete dissociation of weak electrolytes occur. For this reason, the number of ion will be increased. For this reason, the conductance will be increased. But for strong electrolyte, the number of ion is not increases. With the dilution, the number of ion is not increases, but since the volume is increases, the space of the or interionic distance is increases. For this reason, slowly the conductance also increases. Okay? So this is for weak electrolyte and this is for strong electrolyte. Okay? So these two graphs is very important for the strong and weak electrolyte. It may be acetic acid, it may be KCl, it may be NaCl, no problem. It may be ammonium hydroxide, no problem, weak electrolyte. And what happened? And from this question or from this concept, we can calculate the degree of dissociation, that is alpha, or percent dissociation. If it is 100% dissociate, then the lambda is known as lambda 0. If the 100% dissociate, electrolyte is 100% dissociate, then the conductance of the weak electrolyte or strong electrolyte, it will be infinite dilution. The conductance at infinite dilution is known as lambda 0. At any condition, it is known as lambda. Okay, for weak electrolyte, if it is lambda, and at infinite dilution, if it is known as lambda 0, then the ratio of these two, that's mean the strong the lambda at any condition and lambda of the infinite dilution. Okay, then what happened? When it is complete dissociation, that's mean alpha is equal to 1, then this is, and when alpha is equal to alpha or anything, then it is alpha. Okay, so we can say that alpha equal to lambda 0 by lambda. Okay, lambda 0 by lambda, or sorry, if it is alpha infinite, that is lambda by lambda infinite bolte pari etake, lambda infinite or lambda 0. Okay, that is when it is alpha, when it is, that's mean alpha by 1, the ratio of alpha by 1 equal to lambda by lambda 0. This is the condition. Okay, then from the ratio of the conductance at any concentration and infinite dilution, the conductance of a solution at any concentration and the conductance of the solution at infinite dilution, we can get lambda. Okay, so this is the degree of dissociation or percent dissociation. Clear? Now there is a Coldash's law. Scientist Coldash, who is very important in this electrochemistry, okay, who said that this law states the equivalent conductance or conductivity of any electrolyte of infinite dilution is the sum of ionic conductance of the cation and anions. What happened? For any electrolyte, like acetic acid, the conductance of acetic acid plus conductance of acetic acid equal to conductance of acetate plus conductance of H plus at infinite dilution, but it is not at any condition, it is only will be at infinite dilution. Okay, or for strong electrolyte, it will be like lambda of NaCl. We can readily convert that lambda of Na plus lambda of Cl minus. It is always we can write, but this is not always. This condition is only valid for if it is lambda 0, for infinite dilution. Okay, so for infinite dilution lambda, total lambda equal to summation of the cation plus anion of the electrolyte. This rule is known as Coldash's law. So this states the equivalent conductance of an electrolyte at infinite dilution is the sum of its conductance of cation plus anion. Okay, and now if we consider a different salt, that's when let us consider AB type, that's mean AXBY type of salt. Okay, then what happened? Then lambda equivalent, what is lambda equivalent? Lambda equivalent, that's mean lambda of positive, that's mean A term plus, that's mean X plus, lambda of B minus, okay, that's mean B minus Y minus, that is Y minus, or you can write that is charge of, if charge of this is X, then it will be X, it will be Y, no problem. Okay, and what happened? 1 by charge, that's mean Y plus, that is charge of Y and divided by charge of X. Okay, let us consider the real example, aluminum sulfate. Okay, then what happened? That's mean lambda, the total lambda or equivalent conductance of aluminum sulfate equal to 1/3, that's mean 1/3 of aluminum, lambda of aluminum 3 plus, okay, plus 1/2, the charge of sulfate is 2, equal to lambda of sulfate 2 minus. Okay, so this is the equation. Clear? This is the equation. We can write in this way that lambda of aluminum 3 plus by 3, lambda of, that's mean charge, this is the charge, number of charge actually. Okay, so this is the Coldash's law. Now in this way we can get why this Coldash's law is too important, because when it is infinite dilution, then we are unable to get the infinite dilution solution, because up to infinite dilution means if you add water in a solution, then what time it will be infinite dilute, we don't know. For this reason, up to certain dilution, it means 0.001 molar, then this is 1 molar, then 0.5 molar, then 0.25 molar, then 0.12 molar. Okay, in this way, then we are able to get a graph 1, 2, 3, 4, 5 in this way, and conductance also increases. Then what happened? Up to this dilution, then we are unable to get very dilute solution. We can't measure the conductance by instrument, because for very dilute solution we are unable to measure the conductance. Then we will extrapolate this portion. Then this portion is known as lambda 0. Yes, this is the lambda 0. But for infinite dilution, for weak electrolyte, we are unable to get the lambda 0 value, because for infinite dilution this is very high, but there is no cut point. Okay, so for weak electrolyte we are unable to get lambda 0, but for strong electrolyte we can extra plot and we will get the cut point in y-axis and we will get the lambda 0 value. For this reason, a weak electrolyte can be converted to strong electrolyte and we can get the conductance of weak electrolyte. How? Let us consider lambda 0 of lambda of acetic acid. If we write in this way that lambda of CH3 COO Na, so this is strong. This can readily convert in this way that acetic acid, this is acetate plus lambda of Na plus. Now, if we convert this equation for the acetic acid, how we can get? Then we can add HCl and acetic acid and sodium chloride, sodium hydroxide, no problem. That is lambda of Na plus, lambda of Cl minus plus lambda of H plus, lambda of Cl minus, lambda of acetate. Okay. Now this equation, if we convert in this way that lambda of acetate plus lambda of H plus in terms of, that is lambda of Na plus plus lambda of Na plus plus lambda of Cl minus, lambda of Cl minus. Then what happened? What happened? That's been lambda of acetate plus lambda of Na plus. This is actually lambda of acetic acid, sodium acetate plus lambda of plus lambda of H plus lambda of Cl minus, then minus of lambda of Na plus minus lambda of Cl minus. Then what happened? This is H plus, that is HCl, this is NaCl. Okay, if we consider in this way, then this, that's been Cl, Na, its remains is just HCl, that's been acetate, only acetic acid is there. So this is the combination of, this is a strong electrolyte, HCl is a strong electrolyte, NaCl is a strong electrolyte, sodium acetate is a strong electrolyte. So summation of lambda of acetate plus lambda of Na plus lambda of HCl minus lambda of HCl. So these three are strong, but this one is weak. So in terms of strong electrolyte, we can get this, because this equal to this, because this portion is cut out, then remains only lambda of acetate plus lambda of HCl. Okay. So with the help of the three strong electrolyte, we can get the lambda of weak electrolyte. So this is the utility of Cold-Last law. Okay. Now the last portion is Faraday's law. What is the Faraday's law? Faraday states that for electricity or the charge carried. Okay, charge carried. There is a two law. One is first law of Faraday and second law of Faraday. First law of Faraday, the amount of substances deposited or dissociated of an electrolyte at the cathode or anode is directly proportional to the charge or the quantity of charge in coulombs. Okay, what is this? The amount of substances which is deposited in cathode and anode is directly proportional to the charge carried on the cathode and anode. That is Q. Charge is Q amount and amount of substance deposited on cathode and anode is W. So W equal to, what is this? There is a value that is directly proportional to Q. Q is the charge, which is equal to the charge. What is the charge? The value of charge, that's when Q equal to current into time in second, ampere into second. This is the coulomb. Okay. Now W equal to Z into Q. That is, there is a proportionality constant which is known as electrochemical equivalent, where Z is the electrochemical equivalent. And what is the electrochemical equivalent? Z equal to actually E equivalent per coulomb. Equivalent per coulomb. What is this? E is the equivalent weight and F is the Faraday. F, what is F? Equivalent weight, that's when E is equivalent weight. Equivalent weight divided by 966500 coulomb. This is the coulomb. The charge of 1 mole electron. The charge of 1 mole electron is 96500 coulomb. Okay. So equivalent weight per 96500 coulomb is known as Z. That is electrochemical equivalent. So this is the first law of Faraday. Okay. Now, if there is a problem, okay, what was the problem? If we consider a problem that equivalent conductance, if we want to not equivalent conductance, if we want to get the volume or of sodium Cl or chlorine, how many, write it down, how many ml, how many cc of chlorine gas deposited what by 100 ampere current. Okay, 100 ampere current, এই 100 ampere current flow হয়েছে through or following up to 5 hours. Okay, 5 hours through NaCl solution. NaCl solution. Okay, so we know Q equal to IT. So what was that? This is actually I is 100, 5 hours, that's mean Q equal to 5 into 60 into 100. This is coulomb. Okay, and W W equal to equivalent weight into equivalent weight divided by, that's been Z into Q. So Z, and what is the equivalent weight? What is the equivalent? 35.5 for chlorine, 35.5 divided by F, that is 96500 coulomb, and this is actually Z, then into IT, that is 5 into 60 into 60 into 100. Okay, this is gram. Okay, this is actually 662.5 gram. Okay, now you know 71 gram equal to 1 mole or 22.4 liter. You know it about 71 gram equal to 2.4 liter, then 662.5 gram equal to actually 2008.9 liter. Okay, so this amount of chlorine will deposited in the anode. Okay, now what is the second law of Faraday? What is the second law of Faraday? The second law of Faraday states that the amount of any different substances deposited in electrode at any electrode by passes of the same amount of electricity are directly proportional to the equivalent of the substances or equivalent amount of the substances. So W is directly proportional to the equivalent weight of the substances when the same amount, let us consider that for electrolyte the equivalent weight is E1 and the substance must be equal to W1 is deposited is directly proportional to E1, that is W1 is directly proportional to E1, and if the equivalent of a substance is E2, then W2 is proportional to E2. Okay, if the same amount of electricity is passed through. Okay, same amount, that's mean the amount of different substances deposited at any electrode by passage of the same quantity of electricity is directly proportional to the equivalent weight. That's mean if W2 amount of substance is deposited, then W2 is directly proportional to E2. That's mean if the different substance is deposited, then W2 proportional to E2 and W1 proportional to E1. Then if the same amount of current is passed through, then W2 by W1 we can write in this way that E1 or E2 by E1. No problem? Clear? So this is very important. That's mean the W or W is directly proportional to IT into E. What was that? That is W. If proportionality sign is removed, then W we can write in this way, W equal to, what was that? That is Q. The Q is the amount of charge carried, that's mean I into T into E. Clear? So W, what is W? W equal to I into T into E. Then this is very important part. That's mean W equal to IT E by F, where F is the Faraday. Okay, because when IT equal to F, when IT equal to F, then what happened? IT equal to F, then W equal to E. That is, if the amount of the charge equal to 96500 coulomb, then W equal to E. That is, this is very important part. What if 96500 coulomb charge is carried, then equivalent amount of substance will be deposited in cathode or anode. This is very important. That's when 1 Faraday deposited equivalent amount of substances. You know, the equivalent weight of chlorine is 35.5. Then if 1 Faraday charge is carried through the cathode or anode, then 35.5 gram chlorine will be deposited in anode. If the equivalent weight of copper is 31.5 gram, then if 1 Faraday is charge carried, then 31.5 gram copper will be deposited in the cathode. So this is the very important part of electrochemistry. Okay. Thank you.